Welcome back. We are going to spend the next several sessions looking at curve sketching. Now, the reason I say several sessions is because there are so many different elements that we can put in the graph of a function that if we want to draw an accurate graph, there's a lot of steps and it takes a lot of time to do each example. So usually when I were to teach this in person in a 50-minute class, we might be able to get through 2 examples in 50 minutes. It's a very slow-going process, and we want to do several examples so we can see all of the things that go into this and get used to it. But to do several examples, it takes a lot of time. So this is why I dedicate a good portion of a week in my class to curve sketching. Now, I mentioned that there are a lot of things that go into sketching a curve. And here is a list. It's not an exhaustive list. It's not everything that we could put into a graph. But when we're graphing things, we want to make sure we understand what intervals the function is increasing and decreasing on. We want to represent that accurately in the graph. We want to represent any local extreme values accurately, because those are usually some of the most important points on a graph. Especially if this graph represents a real-life quantity, we want to know, when is it its highest? When is it its lowest? When is it increasing or decreasing? All right. We would really like to have the concavity reflected accurately in the graph. We definitely want to know where the inflection points are. If we've got the concavity, the inflection points are where the concavity changes. And then, of course, any intercepts, x-intercepts and y-intercepts, any asymptotes, etc. A lot of these are things that we would never capture simply from a table of values. If we were to make a table of values for a function, that would give us a whole bunch of points, but we don't know if any of those points happen to be local maximum or minimum values. So we don't know when we're drawing the graph if the point that we've chosen that is the highest is actually the highest or not. We don't know intercepts unless we go through and actually calculate those, which you've probably done at some point for polynomial functions or rational functions maybe. And then similarly, asymptotes, those aren't things that we're going to just get from a table of values unless we get incredibly lucky and we're choosing lots of values. So most of these are things that we will use calculus to get. And again, I told you it takes a lot of time to go through examples. And so today, I don't even want to focus on everything here. I want to focus on the things that we get from the derivatives. So increasing and decreasing intervals, local extreme values, concavity, and inflection points. I don't want to worry yet about intercepts or asymptotes unless we luck into some intercepts or asymptotes. We will build those in later, but I kind of want to do this in a scaffolded way where the first examples, we don't do everything. We just focus on the things that the derivatives give us because that's what we've been looking at. And then we start to build in other things like intercepts, asymptotes, other end behavior, etc. So let's get into our first example. Discuss the graph of f of x equals x times 6 minus x to the 2/3 power with respect to concavity, points of inflection, and local extreme values. So if we're going to want concavity, points of inflection, and extreme values, we're going to want to take the first and second derivatives. So let's start with the first derivative. We have f of x as a product of 2 functions. So we're going to have to use the product rule here. So we take the derivative of the first function, the derivative of x is 1, times the second function, 6 minus x to the 2/3 power, plus the first function, which in this case is x, times the derivative of the second function. And this is a composition of functions, so we have to use the chain rule. The derivative of u to the 2/3 power is 2/3 times u, which in this case is 6 minus x, to the negative 1/3 power, because remember we subtract 1 from the exponent. 2/3 minus 1 is negative 1/3. But then we have to multiply by the derivative of the inside, and the derivative of 6 is nothing, but the derivative of negative x is negative 1. So let's look at the first term. 1 times anything is itself. So this is 6 minus x to the 2/3. And then the second term, we've got this negative 1 out front. So this is actually going to become minus. And when we've got a negative exponent, we move something to the denominator. So this is going to be 2x over 3 times 6 minus x to the 1/3 power. Now, we can combine these into one fraction by getting a common denominator. And there's something really cool here. On the left-hand side, I'm just going to write this over 1 for now. If we want a common denominator, we're going to have to multiply the numerator and denominator by 3 times 6 minus x to the 1/3 power. And that's not difficult at all. We are perfectly capable of that. But here's the interesting thing. When we multiply the numerator by 6 minus x to the 1/3 power, we'll put the 3 out front. That's perfectly fine. But when we look at the rest of this, when we take 6 minus x to the 2/3 times 6 minus x to the 1/3, that's 6 minus x to the 3/3, which is just 6 minus x to the first power. So that works out really nicely. And then we have minus 2x over that same denominator. And then we can combine these into one fraction with that same denominator. And I'm going to just do the numerator in my head. 3 times x is 18 minus 3x, and then minus another 2x. That is going to be 18 minus 5x. So this is what we get when we take the first derivative. And we're going to have a couple of critical numbers. The derivative is undefined when x is 6. So we're going to have a critical number at x equals 6. And then the numerator is 0 when x equals 3.6. So that's going to be our other critical number. So those are the two possibilities for local maximum and minimum values for our function. So we're good so far. We can make a sign chart here to get an idea of when our function is increasing or decreasing. So the critical numbers are 3.6 and 6. And then the factors in our derivative are 18 minus 5x, 3, which is always going to be positive, so that doesn't really affect things, but we can include it. And then 6 minus x to the 1/3 power. All right, if we look at 18 minus 5x, that is 0 when x is 3.6. And when x is larger than that, this becomes negative. And when x is smaller than that, this becomes positive. Now we also have this 6 minus x to the 1/3 power. Remember, 1/3 power is just taking a cube root. And when you take the cube root of something, it doesn't affect whether it's positive or negative. So this is really going to have the same signs as just 6 minus x. That's 0 at 6. And then if x is bigger than 6, it's going to end up being negative. And smaller than 6, it's going to be positive. So our derivative is going to be positive, negative, and positive. So it's going to be increasing and then decreasing and then increasing. And so that's going to give us a local maximum at 3.6 and a local minimum at 6. So we're doing well. We've got some important information for our graph. We've got the increasing and decreasing intervals, and we've got the location of the local extreme values. We haven't plugged those in yet to get the function values, but we can do that now. I am simply going to use a calculator to do that. If we plug in 3.6, our function value is going to be approximately 6.45. So f of 3.6 is approximately 6.45. I'm just plugging this into the original function. And then when we evaluate this at 6, that ends up just being 0, because that gives us a factor equal to 0. So we've got a local maximum at 3.6, comma 6.45. That's a maximum. And then a local minimum at 6, comma 0. So we're doing well, but we still don't have concavity and inflection points. For that, we're going to need the second derivative, which is going to require the quotient rule, because the first derivative was a quotient. And this video is already quite long, and I am running out of space here. So what I'm going to do is I'm going to leave that derivative as an exercise for you to do on your own. And I am going to give you the derivative just so that we're not spending time doing that calculation. We end up with 10x minus 72 over 9 times 6 minus x to the 4/3 power. We can see that we're going to get one critical number from the denominator. If that equals 0, that's going to happen when x is 6. So one of our critical numbers here is 6. And then in the numerator, this numerator is 0 when x is 7.2. So we've got to check what's going on at 6 and 7.2. And again, I'm going to make a sign chart so that we can figure out when this is going to be positive and when this is going to be negative. So our factors are 10x minus 72, 9, and then 6 minus x to the 4/3. Now 9 is always going to be positive, and so is 6 minus x to the 4/3. Remember that raising something to the 4/3 power is taking the cube root and then whatever that is, raising it to the 4th power, and anything to an even power is going to be either positive or 0. It's going to be 0 at 6, otherwise it's going to be positive. So those are always positive. And then for 10x minus 72, that's going to be 0 at 7.2. And then if x is larger, it's going to be positive, and smaller, it's going to be negative. So our second derivative is going to be negative, negative, and positive. So that means we're going to be concave down, and concave up. And we've got an inflection point at 7.2, a point of inflection. We'll call that a POI just for short. Now, we already know that the function is equal to 0 when x is 6. We've already calculated that. We have not yet calculated the function value at 7.2. We should do that because it's an important point on our graph. It's a point of inflection. So we will use a calculator for that as well. F of 7.2 is equal to 8.13. All right, so we've got our inflection points and our local extreme values, and we know what's going on with the intervals increasing and decreasing and the concavity between those. Let's put this on some axes. All right, so what do we have? The points that we have are f of 6 equals 0. So that's the point 6, 0. And we said f of 3.6 was about 6.45. So that is, let's see, 1, 2, 3.5, 3.6, and then 6.45. 1, 2, 3, 4, 5. Each of these is 2. So 2, 4, 6.45 is right around there. Let's plot that. 2, 4, 6.45. Something like that, I think. All right. And then we also, we can also do intercepts really quickly. The original function is equal to 0 when x is 6 or x is 0. So that also gives us 0 as an x-intercept, which then also becomes the y-intercept. So that's nice. And then we lastly had a point of inflection at 7.2, comma 8.13. So that's just after 7 to the right, and then after 8 going up, which is around right here. Takes a little bit of mental gymnastics just because the scales are different. The x and y scales are going to be different. But and then what is going on in each of these intervals? We can include this information if we want at the bottom of the graph. We know that the function is increasing up to 3.6. So the function is increasing in the intervals up to 3.6. And then it's decreasing down to 6. And then it's increasing in these other intervals. I usually try and write these little guidelines for myself underneath the axes, but I didn't give myself room here. So that's why I'm writing them there. And then for the concavity, it's concave down all the way on the left of 7.2 and then concave up to the right. So it's concave downward over here, downward, downward, and then downward between 6 and 7.2, but then it's concave upward there. So let's try and draw this. So we know that this point here is a local maximum, and this point here is a local minimum. So we're going to be increasing up until there and then decreasing here. And it's going to be concave downward both. So it's kind of going to be bowl-shaped up and then down. Let's go ahead and draw those in. Okay, but then it's interesting because here it's going to be increasing. So from here to here and then onward it's going to be increasing. And at first it's concave down, which is like a frown. So it's decreasing, but like a frown. And then over here, it's concave up. So it's going to be increasing, like a smile. And so what this is going to look like is increasing and concave downward, and then it changes to increasing and concave upward. And then on the very left-hand interval, the function is increasing from left to right. So as we go from right to left, it's going to be going downward. And it's also concave downward. So it's decreasing in kind of like a frown in a way. And so it's going to look something like that. And that is what I got with the graph. If we compare this to what we get if we use Desmos, let me show you. Boom. There's the graph straight from Desmos, and you can see that it looks quite similar. And that took us 18 minutes. I guess a couple of those minutes in the beginning were explanation. And we didn't even go through and spend time taking the second derivative there. So these problems take a long amount of time, which means that the videos for this section are going to be long. And I'm sorry for that. That is all we can do. But the one nice thing that I'm trying to do to counterbalance that is I'm spreading them out over the course of several lessons. So instead of having to watch 10 of these videos for a single lesson to try and squeeze it all in, we're going to spread things out over the course of a good portion of a week. So there we go.